Welcome back. What we'll do today in this segment and perhaps two more is look at a few boundary value problems. I said few, well, we'll look at one proper boundary value problem, but before that we'll set up the general form of initial and boundary value problems for problems in continuum mechanics. Okay? So what we're going to do today is look at initial and boundary value problems in continuum mechanics. All right. Okay. So essentially what this means is that we put down the governing equations, the governing partial differential equations. We put down at least the general form of any constitutive relations we need. We talk about initial and boundary conditions. Okay, and in principle, once all of this is done, we have the elements needed to go ahead and solve particular problems. Okay, now I'm going to try and give you a combined presentation here for solids and fluids. Okay, all right. So the problems that we're trying to get to are the following, right? We want to find rho, okay, the mass density, x comma t, right? And to sort of overstate the case, this is a mapping from the current configuration across the time interval of interest to R plus, right? You want to find that field. And we also want to find another field, right? We want to find either the displacement field, okay, which is parameterized typically by capital X and T, right? The reference position and time. And this is a mapping from omega naught cross 0 comma t to R3, or for certain problems, instead of saying that we want to find the displacement, it is more appropriate to ask for the velocity, okay? And the velocity field in this case would be the spatial velocity field, okay? And this is a mapping from the current configuration cross time interval to R3 as well, okay, vector. Okay, and you recognize now which problems we're talking of when we put down the second line right here, right? When we say that we want the displacement field, we are really thinking of problems of solid mechanics, okay? And when we say we want the velocity field, we're typically talking of fluids. Okay, typically. Of course, they're interchangeable, and in some special circumstances, we may change that around, but typically not, okay? So, and the reason this works out this way is that for solids, we have the reference configuration, it deforms to the current configuration. We're typically interested, because of this Lagrangian type of description that we follow for solid mechanics, we're typically interested in knowing, okay, basically what is that displacement field, okay? The situation is different for fluids, right? For fluids, we have our our window, right, and our little water tunnel or wind tunnel where things are flowing past, it doesn't really make sense to ask how much has a point been displaced now, how much has a fluid particle been displaced from here to here. We are typically interested in looking at how quickly is the flow going past us, right, and what direction is it going. Okay, so and for that reason, the velocity is more of a natural measure of the solution. Okay, it's a more natural quantity to ask for. All right, but of course we know that they are related, right? We know, of course, that the velocity v of x comma t, we always know this, right? Knowing furthermore that we have this idea of that motion, right? So there is that relation between them. All right, so this is the setting, and let us now look at, these are the fields that we're looking for. What are the governing equations now? I'll write the equations in the current configuration, right? And in the current configuration, we have the following equation for the balance of mass, right? So we want to find the fields rho and u or v such that they satisfy the following equations. Right? Balance of mass. And we have then our balance of linear momentum, right? The balance of linear momentum we write as rho times the material time derivative of the spatial velocity, and we are writing it out explicitly as a partial time derivative plus the convective term, okay, equals divergence of sigma plus a body force, right, in omega t cross 0 comma t. Okay, so those are our governing equations, our governing partial differential equations. Now, of course, you observe that we have fields showing up here that are not already part of our primal fields that we're trying to seek solutions in terms of, right? So we have things showing up here which don't reflect u or v or anything, right? So let's just say what they are. So we've already done some of that. We've already said that the velocity is obtained as the time derivative of the displacement field, right? What about the other ones, right? Let's just put down those sorts of things. Okay, so where we have, okay, in the context of solids, we have, I should say for solids, right? For solids, we have, first of all, we need to say that F equals 1, our isotropic tensor, plus partial derivative of the displacement with respect to the reference position. Okay? And then, since we are working in terms of the Cauchy stress, we also say then that the Cauchy stress, sigma, equals 1 over determinant of F, okay, derivative of some function psi of F with respect to F multiplied by F transpose. So we have this relation for the Cauchy stress, where we know where for F equals RU, right, where again R belonging to SO3 plus, U belonging to S3 plus, right? So R is an orthogonal rotation tensor, U is a symmetric positive definite tensor. So, right, for these conditions, we also have psi of F has to be a function of F only through the right stretch tensor. Okay, so that is our condition of frame invariance. All right, so this is the situation that we have for solids. Okay, for fluids, right, for fluids, what we say is that sigma equals, in the most general form, we could have a pressure term, okay, plus a viscous stress, right, where the viscous stress we know is a function of D. Okay. Furthermore, what we can say is that where sigma V of D is such that sigma V of Q D Q transpose has to be equal to Q sigma V of D Q transpose Q belonging to SO3. All right. Well, it holds for all Q belonging to SO3, but we typically look at rotations that preserve the handedness. All right. So we have these conditions, and now we could get more specific about the pressure term, but that really requires more specifications on the form of the mass balance equation, so we won't get into details about compressibility or incompressibility and so on here. Okay. We have a pressure term which may or may not have another constitutive relation for itself. Okay, but this is the very minimum that we need in terms of constitutive relations, right? Again, and we know that this condition also is frame invariance, right? So this condition also is frame invariance or objectivity, as we have often also called it. Okay, so those are the constitutive relations, and so I should probably state that here, right? So this is a constitutive relation okay, and so is this, right? This is also a constitutive relation. Okay. Okay. So we have all this. So we've laid down we've talked about the fields we want to solve for. We have our PDEs. We've laid out constitutive relations to give us connections between the primal fields, the density and the displacement or velocity, and these stress fields, right? We know all of this. Well, okay, I guess this is not entirely complete because I didn't say how we get d from the velocity, right? Where we know that d now is the symmetric part of the spatial gradient of the velocity field. Okay, that completes things. Okay, so much for constitutive relations, right? Let us talk now of boundary conditions. Okay, so boundary conditions. All right. So the boundary conditions here that we use are the following. Right now, in the case of solids, right? In the case of solids, we first of all say that the boundary can be split up into a displacement boundary and a traction boundary. And I don't truly need an underbar here. Okay? So the total boundary is properly the closure of those two boundary subsets because both of them are open subsets and we want to make sure we get all the limit points. Okay. So for this step of a decomposition of the boundary, right, we have u equals u bar on the displacement boundary, right? Go to the next slide. And we say that sigma n equals T on partial of omega T traction, right, on that part of this, on that subset of the boundary. Okay, so this is our traction boundary condition in the context of solids, right? And we know what n is the unit normal and so forth, right? Right? It's a vector of unit magnitude. All right, so this is what we have in the case of solids, right, for boundary conditions. For fluids, okay, for fluids we have a similar decomposition. We have a decomposition of the boundary into what we will call a velocity boundary and a pressure boundary. Okay, this kind of a decomposition is typical in the case of fluids. Okay, what we have then is that the velocity equals some known velocity on that boundary. Okay, and the pressure is some known pressure on the pressure boundary. All right? Okay. Finally, we observe that the equation that governs the balance of linear momentum is properly a partial differential equation including time dependence, right? It has time dependent terms on the left-hand side, okay? Right, let me just get back to 2 slides and point that out, right? So we have these time dependent terms here, right? So it follows that we need to account for initial conditions, okay? Now, okay, so let's talk about initial conditions. So again, let's talk about solids first. All right. Now that partial time derivative I circled, going back a couple of slides, has the following form, right? We have partial of v with respect to time. But remember, really, in the context of solids, our primal field is the displacement field, right? So this becomes okay, the acceleration, right? Consequently, what this means is that we have two derivatives, right? So what this means is that we have a differential equation, a partial differential equation that's second order in time for the displacements. Okay? Consequently, we need two initial conditions. Okay? So what's typical is to say that the displacement at a point at the initial time, right, time t equals 0, equals u naught function of x alone. Okay? What this means is that now, looking back at the displacement field parameterized with respect to reference position, we're saying that the entire body is, the points have a certain displacement, right? And it's typical, of course, in the context of solid mechanics, because we tend to think of this as the initial position. It's typical to require that at time t equals 0, the displacements are fixed somewhere, right? So we typically say that the displacement is 0 at time t equals 0, okay, because we measure the displacement from here, okay? So that is a typical condition. And then we need another condition, right? The second condition, again, is typically that on the velocity, okay? So we say that we start out things, and at time t equals 0, since the body is going to start tumbling and deforming and so on, we say, okay, things start deforming with some initial velocity, okay? Those constitute our two initial conditions here, right? So we have this, and then we typically write this as partial of u with respect to time at x comma 0 equals the material velocity, right, as a function of position. All right? So we have those two conditions. For fluids, right? For fluids, it's somewhat simpler because we have already this partial time derivative on the spatial velocity field, which in any case is our primal solution field, right? Our primal field that we're seeking solutions for. So this is first order. Okay, so we really need a single condition, right? So the condition that we specify is typically of the form v at x comma 0 equals v naught function of x. Okay, so we're saying that when things start up in our little water tunnel here, we're saying, okay, when we turn things on, we record the initial velocity, right? And then say, okay, now let things run from there. Okay, those are our initial conditions. Okay, all right. So that really summarizes the initial and boundary value problem, the general form of the initial and boundary value problems for continuum mechanics. And we saw how the fields are slightly different. We take different fields depending upon whether we're talking of solids or fluids. And likewise then how the constitutive relations have to be different, how the boundary conditions and even the initial conditions we pose must be different. Okay, we'll stop here for this segment. When we come back, we'll look at a specific boundary value problem. right? Initial and boundary value problem.